So, can you hear me okay if I speak like that? Yeah, okay. I will keep the talk much shorter than advertised because of this, but as long as you can hear, that's okay. Yeah, okay, all right, thank you. All right. Okay. It's a talk about hidden markup models. All right. Okay, and first, I will talk about this map estimation problem. So the only thing to watch out for here is that the superscript n, the superscript refers to the length of the data record. Okay, that's what you need to know. Is it okay? Yeah, okay. Oops. All right. And there's, so this is the Viterbi process. It was introduced first in the information theory literature in the context of hidden markup models with discrete states, a finite number of discrete states. And in this particular paper, the norm appearing there is the discrete norm, the norm associated with the discrete distance. And they treated the observations up here as a sequence of random variables. And the limit here is an almost sure limit with respect to the distribution of the y's induced by the HMM. Okay. A bit later, these guys addressed the case where the hidden state X lives on the real line, one-dimensional hidden state. And then the norm for them was the Euclidean, that from the Euclidean distance. Okay. For the rest of this talk, when you see this norm, it will be the Euclidean norm. Okay. And the X will live in RD throughout the rest of the talk. Okay. In these papers, the Viterbi process, I think it was just of mathematical interest. Okay, but the starting point for the work that I'll tell you a bit about is that the fact that such a thing might exist has some potential practical implications as well. Okay, so the idea is this. Okay, let's suppose that I want to compute just these first 0 to m components of the map estimator, just the first few components. Okay, well, the existence of that limit suggests that I don't need to know these observations in order to calculate these first few components approximately, right? I just maybe need to know the first m to m plus delta observations. Maybe that'll do, okay? The existence of the limit just suggests that that might be true. Okay, so if indeed I can approximately compute this, only knowing these observations, well then I could also approximately compute the bit over here, knowing only a few observations over here, right? Okay, and in that sense you can break down an approximate calculation of the map estimate into segments of the data which can be processed in parallel, right? So what's going on here? I've not written down explicitly the parallelization scheme with algebra because the indexing is complicated. I just show you this picture, right? So what's going on? Each of these squares, it just means one of the observations there, right? So I split my observation sequence up into overlapping segments where the overlap is controlled by delta. For each of the segments, I calculate the map estimate just on the basis of those observations. I do that for each of the segments. I discard the overlapping bits and I concatenate the answer. Okay? Alright. And so what do I mean by parallelized? Well, it could be that each of those overlapping segments gets put on a separate core on your computer. Right? I think it's not important for the parallelization that each of these things has their own screen, has their own monitor. Right? It's just a picture. Okay. Okay. Is the idea of the parallelization clear? You see what I mean? I haven't written it explicitly because it's messy if I do. But you So then the question comes, well, is it worth it? Right? So if I write big T of n for the amount of time it takes to solve the optimization problem for n observations, well, the best speed up that you can hope for is going to be something like this, approximately, in the best case. And if I want to get some understanding of the error, well, there's a rough order of magnitude. The total squared error associated with the full thing is going to be roughly the number of segments multiplied by the squared error associated with the first segment. Okay, just in terms of order of magnitude. Okay, so what I will talk about then is trying to quantify this error. And you see that that's a similar question to asking for something about the rate of convergence to the Viterbi process as a function of little delta, and perhaps as a function of m and n as well. Okay, and what we'll see, and the objective is to also understand the dependence on the dimension of that rate of convergence. What do I mean, dimension of what? I mean the dimension of each one of these guys, so the dimension of the hidden state. And what we'll see, if I don't give up by then, is that once we've said something about the map estimator, it's natural to, almost with the same tools, say something about a parallelized sampling scheme. You'll see what I mean as we go. Okay, right. So, in interest of my voice, I'm going to skip the application. Sorry about that. Okay, we go straight to some convexity, right? So, some definitions. This definition, if you take lambda to be 0, this just says U is convex. Okay, if lambda is strictly positive, then it's something more than just convexity. It says that U roughly is at least as convex as a quadratic. Okay, and if you assume that C is differentiable, then it's perhaps a bit more transparent what's going on. You see that if C is differentiable, this condition is equivalent to making this approximation in a second order Taylor expansion of U, or equivalently, this approximation in a first order Taylor expansion of the gradient of U. Okay, if you can differentiate continuously twice, it's also equivalent to saying that all the eigenvalues of the Hessian of U are at least equal to lambda. Okay. So I will need to refer to number 2. So let's write that up. Okay, so the purpose of this slide is just so that whenever you see this condition appear, just realize that it's to do with the curvature of U. Okay, it's about U having as much convexity as a quadratic. Okay, so what's next? Okay, so there's another interpretation of that convexity condition in terms of an ODE which follows the gradient of U. Okay, so that's the ODE which follows the gradient of U, and if you have the U is C1 and strongly convex with a particular lambda, well, the flow associated with the ODE is contracting at a rate given by lambda, okay, for any x and x dash, so globally contracting. And to see where that comes from, if you just differentiate the square of the norm of that difference, you get that inner product appearing, right? And you see that inner product there is exactly of this form. Okay, you just substitute in phi t of x and phi t of x dash for x and x dash here. Okay, nice and easy. In fact, you can reverse the implication here, by which I mean that if you assume that the ODE has a solution which is a little bit regular, and you assume that that solution flow has this property globally, then in fact you can deduce that U must satisfy this for all x and x dash. Okay, so one way you can think of this strong convexity condition is that it's exactly the condition which makes the gradient ODE a global contraction. Okay, we'll come back to that later. implications of this convexity condition? Well, let's suppose we're concerned with optimization. Okay, well, we can write down an Euler discretization of that ODE, assuming the same convexity, and also this Lipschitz condition, which is enough to make sure that the Euler scheme is stable. Okay, well, at least for suitably small step size, the gradient algorithm converges exponentially fast. Alright, and one thing that's sort of practically important here is that you see that both sides of this inequality are additive in the dimension. Okay? Because that's an inner product and that's a square norm, so additive in dimension. And so from that point of view, one can think of this lambda as being a parameter which is does not necessarily have any dependence on dimension. Okay? Similarly here in this Lipschitz condition, if you square both sides of that, both sides are additive in dimension. So mu is a constant which is not necessarily dependent on dimension as well. So the convergence rate of your Euler scheme does not necessarily depend on dimension. If you add a bit of Brownian noise to that ODE, well then you get an SDE which admits this density as an invariant distribution. Okay, and an Euler discretization under this strong convexity condition actually does quite a good job of allowing you to sample approximately from pi in this sense. Okay, you can see that there's a kind of term that's appeared over here which has explicit d-dependence which wasn't there for the Euler discretization of the ODE, and that's linked to the randomness of the algorithm in some way. Okay, so Eric and Alan Thomas and some other guys have done some work on refining the analysis of this recently. This is just one version of their results. Okay, so now I try to relate all that back to this Viterbi process thing. So first, I want to think about how you could try to show that this Viterbi process thing exists. Okay, so that's just a reminder of the definition of the map estimator. And one thing that might be tempting to do is that you could say, well, should I think of this Viterbi process as somehow the maximizer of some limiting density, right, as the time horizon goes to infinity? The problem is that, in general, such a density over an infinite time horizon doesn't exist, okay? Because in typical hidden Markov models, the prior over the signal on an infinitely long time horizon is singular with respect to the posterior. Okay, so dead end, you can't do that. But from a slightly different perspective on this optimization problem, you can find something which is not pathological. Okay, so now I introduce the gradient ODE associated with the smoothing density. Okay, and then, well, what we would expect is that the map estimate, of course, should be a fixed point of that ODE. Okay. So then we make this observation about the HMM. This is just the definition of U. The thing that appears up there, right, is additive. And you see the Markov nature of the HMM. And the point here is that if I now start to think about the elements of this gradient vector, so each of these elements is a partial derivative of this form, right? You see that as long as little n is strictly bigger than little m, the right-hand side over here does not have any dependence on little n. Okay? So if you think about this gradient vector and you look at each of its elements, as I take n to infinity, each of the elements of that vector converges to something. Okay? So that seems to suggest that, in some sense, this gradient vector, as it gets longer and longer, converges to something. Okay, perhaps, at least. I'll denote this idea gradient of u infinity. I stress it's not the gradient of the limit of a function, right? It's the limit of a sequence of gradients of functions. Okay, I'll make it precise in a minute. If such a thing exists, well, perhaps we can try to write down a ODE associated with this limiting object and try to characterize the Viterbi process as a fixed point associated with that kind. Okay, so of course this is very vague. What I'm trying to introduce on the next slide is the mathematical formalism to make it a bit more rigorous. Okay, so this is the way. Okay, so I'm going to write each of the x0 here. I'm going to stack them all into one long, infinitely long, in fact, vector x. Okay, right. And I'm going to introduce where gamma here is a parameter between 0 and 1, which I'll return to that in a minute, an inner product and a norm associated with that gamma. So what's going on here is that this norm inside, this inner product inside, that's the standard Euclidean scalar product on RD. Okay? And if you do that in this way, this thing gives you a well-defined scalar product on the space of infinite sequences. Okay? Giving me overall a Hilbert space, which I'll call L2 gamma. Right? It's a Hilbert sequence space, just where what I've done is introduce some weighting into the scalar product. Okay? Right. So under some conditions, which I'll maybe talk about in a minute. Okay, I don't want to show you the assumptions first because they're too complicated. I'll show you the statement first, we'll talk about the assumption after. This is the idea, right? Okay, so here you can see I've got my gradient of un, and I pad it out with zeros to make an infinitely long vector so that it can live in the right space. Okay? So under some conditions, there is a limiting map from L2 to itself, a limiting vector field to which this thing converges as n goes to infinity. Okay? Moreover, under conditions, which I'll show you in a minute, the limiting vector field u infinity satisfies a condition like this. You see that all it is the same as this thing. Okay? But now I'm on my Hilbert space using my weighted scalar product. Okay? And once I've got this condition, well then, I can construct an ODE on the Hilbert space. Okay, so Frege ODE in this context just means that the limits that define this derivative are with respect to the norm on the Hilbert space. I've got an ODE basically on the Hilbert space, and because I have this property, or by the same arguments that I showed you before about ODEs, I have this contraction property, and so I know that there must be a unique fixed point of this flow, right? And this thing, psi infinity, is what I want to eventually be the Viterbi process. Okay? Makes sense? Okay. So, this is just a kind of complicated way to obtain this fixed point, right? Okay, so once I've got this object, so I want to verify that it is indeed the Viterbi process now. So what does that mean? That means I want to be able to say that the map estimators on a finite time horizon converge to it. So I'm going to do that in the Hilbert space as well. So I take my map estimate and I pad it out with zeros so it lives in the right space. Okay? And then, at least again under some conditions, I can obtain a bound on the norm in the Hilbert space that looks like this. So the important thing here is that the gamma, right, which was remember gamma was between 0 and 1. It was the scaling in my norm. I've got that raised to the power n up there. So there's hope that as n goes to infinity, this term will get killed off. Okay? Similar story here with particular constants which depend on the model. Right? And if you look what's going on here in beta n, when I do this evaluation, in fact the only way that beta n depends on n is through yn. Okay? So if, for example, the y-ends were random and were a stationary sequence, this beta n would be a stationary sequence. Okay, and so for this to go to 0, I need for that stationary sequence to get killed off by this exponential decay there, which happens almost surely in the limit, at least for a certain class of stationary processes. Okay. Okay, so I want to say just a little bit about the proof of this bound, because it will be relevant to something in a moment. I don't expect all the details to be transparent, but I just try to show some of the key steps. Okay, so this is my ODE now on the Hilbert space, and this Viterbi process is the fixed point of this guy, right? And I'm going to cheat a little bit with the notation. I'm going to assume that I've my gradient of UN, again, I've padded it out with zeros, so that this ODE lives in the same space as well. Okay, right. And so I now want to compare the fixed points, basically, of two ODEs that live in the same space, right? And I'm going to do that via these two equalities, right? So here I've just used the fact that I know from the previous result that this thing must converge to this thing, right? And here I've just used the fact that psi n is a fixed point for this guy, right? Okay, so what I need to do is that I need to compare the trajectories of two ODEs started from the same location, right? Perhaps unsurprisingly, when you decompose that, what appears is a difference between the vector fields of those two ODEs. Okay, don't worry about the details. The main thing is the difference between the fields of those ODEs that appears. Okay. And then moreover, if you remember, how did we get to this object in the first place? Well, we said that each of the elements of this vector field converges to the element of that as n goes to infinity, right? So as n grows, this thing is going to go to 0, right? And in fact, because of the way that the weighting with the gamma comes in, that's what gets me this gamma to the power n up there. Okay, so I've got two ODEs, and at least on the early part of the time horizon, the components of their vector fields on the early components are the same. The only difference is down where n is large, and this norm on the Hilbert space penalizes that bit, right? Which is what gives us the gamma to the end there. Okay. The alpha n and the betas and the lambdas, they come from some other terms here. It's messy, so I won't talk about that. Okay. Right. Am I okay for time, AJ? Yeah, all right. Let's have a bit of... Okay. So, this is what I asked for at the beginning, right? I asked for something about this error. And once I've got the previous result, then I can deduce something about this too. And I get an error bound, which looks like this. Okay, so what's important here is that I've got my gamma raised to the power delta. What was delta? It was the amount of overlap between the segments. So as I increase delta, I increase the overlap. It kills off this error exponentially fast. Okay. You see, it's the same stuff with the alphas and betas appearing as before. Okay, but the crucial thing is the gamma to the power delta. Right. I'll say just a little bit about the conditions. Okay. So, in order to get something like this, it turns out, perhaps not too surprisingly, that I need something a bit stronger than strong convexity of the smoothing density, right? So I need this, okay, and something a little bit more. And what is that something a little bit more? Is the thing that allows me to work in this gamma norm, okay? And it's to do with the correlation structure or the strength of dependence in the HMM over time. So this slide's a bit complicated, but just to give you a quick taste. So let's assume I've got a state space model like this, okay, where the observations come from some density. Well, I can balance different ingredients of the model to achieve the conditions that I need. Okay, so if the signal is linear Gaussian, but not necessarily ergodic, okay, then it's sufficient for the observation likelihood to be sufficiently strongly log concave. So basically, the log concavity of these likelihood terms is enough to make things work. And if I don't want to assume a log concavity of the observation density, I can relax what happens with this parameter here from being strictly positive to being possibly negative. So that allows the curvature of the log likelihood terms to go both positive and negative, so they could be multimodal. They don't have to have exponential tails. I can do that if the signal is sufficiently stable, basically. Right. And lastly, it's not necessary for things to be Gaussian. That just makes it easier to illustrate. For example, if these things are Lipschitz, then again, sufficiently strong log concavity of the likelihoods will be enough. Okay. Okay, so it's right. One last comment about the conditions. So I said earlier on I wanted to say something about the dimension dependence of that rate. So it comes down to asking about the dimension dependence of gamma, right? Because gamma raised to the power delta was what gives me the convergence to the Viterbi process. And at least in situations that are simply enough that you can do some fairly explicit calculations, you can show that that gamma does not necessarily have any dependence on dimension either. Okay, so for example, in this nice easy case where the signal is linear with just the scalar in the front, so a really nice simple AR1 process, I can actually take gamma to be just the modulus of, the absolute value of A, hence not having any dependence on dimension at all. Okay, so the nice thing about that is that then over here, my lambda does not necessarily depend on dimension. The gamma does not necessarily depend on dimension. Remember, the beta came from the square of the gradients, so that might be linear in dimension, say, but it's not too bad overall. Okay, so last little bit. Right. So the story with the Viterbi process, as I've told it, was that sort of one of the ways that you can think about what the Viterbi process is to think about the relationship between this sort of finite dimensional ODE and the limiting infinite dimensional one, right? Well, if you can think about that, then you can also think about some relationship between the corresponding SDEs, right? So now let's say that once again I've padded out the gradient of UN with zeros so that these two ODEs live in the same space and these two SDEs live in the same space as well. And now let's say that I take the same Brownian motion in each of these. So to be clear, this Brownian motion is an infinitely long vector of one-dimensional Brownian motions. Okay. Okay, well, perhaps then I can parallelize Euler sampling as well, right? What I'd like to be the case now is that the path of the diffusion or its Euler discretization, which targets the full posterior density, I'd like to be able to approximate the early components of that using only a small subset of the observations. Okay? And what that comes down to is asking for something like this. Okay, but now for the solutions of the SDE rather than the ODE. And in fact, because the Brownian motions are common to the two, it's possible to get an expression for the SDE solution which looks almost exactly like this, it turns out, on paths of the SDE. So it's an almost sure comparison of the paths of two SDEs expressed just in terms of the difference between their two drifts. Okay? Okay, so in terms of algorithms, what would that look like? So what have I done here? I've written down a family of Euler algorithms, okay, all with the same Gaussian random variables driving them, okay. So once again, I stress that the gradient of UN here is padded out with zeros down to infinity, right? So this is a synchronous coupling of Euler algorithms, okay. Here's my observation sequence. Here's the random numbers which are common to all my algorithms down here. And what I would like to show is that these early components of the Euler algorithm, which targets the full smoothing distribution on the path of the algorithm, is approximately equal to these components of the path of the algorithm just targeting this smoothing distribution. Okay. And in fact, you can do the analysis on the SDE, or you can do it directly on Euler. It's actually a little bit easier on Euler directly. At least if you assume, as perhaps you would expect, something like some kind of Lipschitz condition which mimics the kind of thing we had in the finite dimensional case. Alright? So I realize this is a bit messy, but this is basically, once again, the sample error, the error between the samplers associated with just the first segment, right? This is the Euler that targets the full smoothing distribution. This is the Euler which just targets the first few observations, okay? And I can say something about how far apart those random variables are. So this is an almost sure inequality, and there's just one random thing here. Everything else is constant. There's just one random variable, but which is, as an expectation, bounded uniformly in an appropriate sense. Okay? And the good thing again is that once again I've got my y over delta there. So that as I increase delta, it kills off the error. I think I'm gonna leave it there. But thanks for listening.
I think we're only 4 minutes. 2 questions at most.
Yeah, sure.
That's okay.
Yeah. Or maybe not. That's fine.
No, I'll excellent. How different is your new set of assumptions from the Chigansky and Ratorsky?
Yeah, so they assume that the P of y given x is strongly log concave, and I don't need that. So at all. Sorry. So they require that. I don't.